All right, so this is the 6-5 lesson rational root theorem. I just wanted to throw the vocab up again in case I went too quick and you missed something. So if there's any notes you want to jot down here, go ahead and hit pause. And then quickly to run through the types of factoring that we saw. Always look for GCF first. So in example 1, we ended up with a quadratic function after we pulled out the greatest common factor. And the quadratic function didn't factor, so we had to use the quadratic formula to solve for the roots. The second example was a group factoring by grouping, which we've seen before. So we factored by grouping and then found the roots on that one. Third type of factoring is the pattern where if the leading degree, the highest degree, is twice the next highest, and it's a trinomial, then you can factor it with the t-chart or the AC method. So when you see a trinomial, even if it's not a quadratic trinomial, look for that pattern to see if you can factor it with one of the ways that we already know, and then keep factoring in order to get that solved. Example 2b was where we ran into the rational root theorem. Alright, so there's something wrong with my smartboard and the interactive piece isn't working real well. So you're going to be seeing that pen come up every time I write, which is kind of annoying. But I couldn't figure out how to fix it. And it's Saturday, so there's no one here to help me. Alright, so we first of all get this set equal to 0. So get all of your terms on one side of the equal sign. And then it's a quadnomial, so we thought about factoring by grouping, but this one didn't work out to factor by grouping. So we did pull out the GCF. And then we had to use the rational root theorem. So we look at the leading coefficient and the constant. The constant is what we look at first. The factors of the constant will be the numerator. The factors of the leading coefficient will be the denominator. Nice that in this case our leading coefficient is 1. So all we have to worry about are the factors of our constant. So the factors of 12, are positive and negative 1, 2, 3, 4, 6, and 12. If you have a graphing calculator, it's very helpful. You should use that to see which one of these roots might possibly work for us. Jack had a very nice graphing calculator app. I've still got the name and the creator of that listed for graphing calculator if you want to look for that one. Otherwise, if you do intend to continue with math, especially into college, it's a really wise investment to get a graphing calculator. Not to plug this, but I know Mr. Swenson sells them for like 20 bucks. So if you can't find them on eBay for cheap, I know they're really expensive to buy them new. You can talk to Mr. Swenson. I don't know where he gets them, then that he can sell them that cheap. But that's something to think about for if math is something you plan to take. It'll be really helpful for pre-calc next year as well. All right, so if you have a graphing calculator, look for the roots there so that you can really narrow this down and get it factored. Otherwise, you're just going to have to guess and check. I think we had looked at 1 being one of the ones that worked for us. So we set up our synthetic division. The coefficients of our polynomial 1x cubed, negative 2x squared, negative 11x, and positive 12. Make sure you get all of those coefficients in there. If one of them's missing, make sure you throw 0. Bring down the 1, multiply, add, multiply, add, multiply, add. So what you're looking for is that remainder of 0 to know that it goes into that polynomial exactly. So as I continue dividing this, don't lose that common factor we already had. Now what this means here is that 1 is a root, which means x equals 1 is a solution of the polynomial. So when you set that to 0, you subtract 1 from both sides. So the x minus 1 is the factor of the polynomial. So make sure you think about that asylum piece. And then remember we use the results from the synthetic division to get the coefficients of what's left after we factored out that x minus 1. So we drop a power on the cube, x squared minus x minus 12. Now we have a quadratic, so we can either continue factoring or use quadratic formula to solve. This one does factor. Just a t-table factoring on that one. 3 plus negative 4 is negative 1. 3 times negative 4 is negative 12. And then we set each piece equal to 0 to completely solve. We already knew x equals 1 was one of our results. X equals negative 3 and positive 4 are the other two. Alright, so our last example, we ran out of time to completely finish this one in class, but when we looked through, we didn't find a greatest common factor, so we looked for rational root theorem. Luckily enough, our leading coefficient was 1 again, so similar to the last one, we only have to worry about those roots of 150. The factors of 150. But there are a lot of them, so that would be a lot to guess and check. So we tried graphing it, and we noticed that I think it was both positive and negative 5 worked for roots. And I think when I did this one, 5 was one that I guessed anyway, and I think I was thinking that 25 is a multiple of 5, so maybe 5 will work for us. So when we set up our division, this time I'll use a negative, just to remind us how that works. Set up your coefficients for all your terms. We're not missing any this time either, so we've got 1x to the 4th, negative 1x cubed, negative 31x squared, positive 25x, and positive 150. So we bring down the 1, multiply, add, multiply, add, multiply, add, and multiply. We get that nice remainder of 0, which means that negative 5 is a factor of this polynomial. So we start to factor. Remember, when we put it back in, it goes in the asylum, so it's the opposite of what we divided out. So what's left, we use those coefficients that we got when we used our synthetic division. Drop a power, so x cubed minus 6x squared minus x minus 30 equals 0. Now I'm going to look at what's left. Can I factor it some other way? Because the rational root theorem isn't always the easiest way to get it factored. So I look for factoring by grouping on this one. I'm still not seeing those coefficients work for me, so I do have to use that rational root theorem again. You don't have to start all over. We already know all of the possibilities. And when we looked at the graph, I think we noticed both positive and negative 5 worked. So this time I'll divide by positive 5. 1x cubed minus 6x squared minus 1x minus 30. Bring down the 1, multiply, add, multiply, add, multiply, and did I do something wrong? Because those aren't adding to 0. So maybe 5 wasn't a factor. Just checking my signs here to make sure I didn't lose anything, and I did. Maybe some of you noticed that right here. This is a positive 30, and I wrote negative 30. So this one does add to 0, so 5 does factor as well. So then we got x plus 5 from our previous factor, x minus 5 for this factor, and then we're finally down to a quadratic, which we no longer have to use that rational root theorem for. If that quadratic doesn't continue to factor, we can use quadratic formula for the last couple of roots. However, it does factor. So what multiplies to negative 6 and adds to negative 1 would be a positive 2 and a negative 3. So to finally finish all of our roots, we have x equals positive or negative 5, negative 2, positive 3. All right, I'm also going to take the 6-6 lesson because it's quick and easy, and there's a little bit more solving involved, and that will give us Monday to spend practicing so I can help answer some questions that I didn't have a chance to answer on Friday. All right. So 6-6, fundamental theorem of algebra. We're going to be writing polynomial functions given the zeros. And we have already done this with quadratic functions. Now we're just adding an extra 0 or 2, so the process isn't any different. So we're just going to run through a couple quick examples. Our first one, we have zeros of 2 -3/4, and 4. The integers are easy enough. We just saw what happened when we had a 0. If I have x minus 2 times whatever equals 0, to solve that, x equals 2 would be one of my roots. So quantity x minus 2 is part of my polynomial function. That fraction is a little bit different. So let's think about if we have x equals -3/4, where might that have come from? Because we don't normally see fractions when we write those binomials with polynomials. Well, to solve this, to get it equal to 0, there's a couple of different steps that I can think about. One is multiplying both sides by 4. So 4x equals -3. And then I'm going to add 3 to both sides. So that's what my binomial piece will look like for a fraction. And then I've got my other integer of 4. So here's how I'm going to set up my work for this one. So I had a 0 of 2, so putting that in the asylum. I had the 0 of -3/4. I just found out that could look like 4x plus 3. And then I have a 0 of 4, so putting that in the asylum, it becomes x equals -4. Actually, if we're writing the function instead of saying 0, sorry, I have to touch this. It doesn't realize I'm picking up the eraser. We should say equals y or f of x, or somehow name it with the function name. All right, so then to put this in standard form, we just multiply it out. So I am going to multiply x times 4x times x to give me 4x cubed. These are the partial products that I showed when we were going over the binomial expansion. So if you can't quite follow this, then just multiply your first two binomials and multiply by the third binomial, and that's fine. I try and get this done all in one step. So then I distribute the x to the 4x to the -4. So you take the first two terms in the first two binomials and multiply it by each of the terms in the third binomial. So the x times 4x is 4x squared times -4 is -16x squared. Now I'm going to multiply the first term in the first binomial with the second term in the second binomial and each of the terms in the last one. So now I'm going to go from x to 3 to x, which is 3x squared. And then x times 3 times -4 gives me 3x times -4, -12x. Alright, so I have exhausted the first term in the first binomial. So now I need to look at the second term and do the same thing. So I've got -2 times 4x times x is -8x squared. And -2 times 4x times -4 is 16 times 2 is 32. Is that 32x? And then I'm going to take the -2 times the 3 times each of the two terms in the last one. So -2 times 3 is -6x. And -2 times 3 is -6 times -4 is +24. So again, if all of that was a bit much for you, just FOIL the first two and then distribute through to the third one and you'll end up with the same answer. So the last thing we need to do is simplify our answer. So I've got a 4x cubed and I've got a -16x squared plus 3x squared is -13 minus 8 is -21x squared. And then I have a -12x plus 32x is 20x, minus 6 is 14x plus 24. So that is our polynomial in standard form with the zeros of, what did we start with, 2, -3/4, and 4. All right, on this one we're going to learn how to write a polynomial function with complex zeros. The key for this is that complex zeros always come in pairs. You can't have a polynomial function with one complex zero. It has to have 2, 4, 6, etc. The other one, when you're only given one of them, is the complex conjugate. So if you remember, the complex conjugate is when you change the sign on the imaginary part. So our polynomial has two zeros, 3 plus 2i and 3 minus 2i. So we're going to set these up in our binomials. So that is the first one. Oh, sorry, that should be an x. And now I just realized I'm putting them in the asylum, so those should both be minus signs, because we're putting them both in the asylum. So one of our zeros is the 3 plus 2i, so we put that in the asylum on my second one here. And then the other 0 is 3 minus 2i, that's going in the asylum as well, and that was my first one. So let me kind of make a note so you guys can follow. And then the asylum is why this was negative, that's the asylum piece. So here's my first 0 going here, and the minus is for the asylum. So what I'm going to do is regroup this so that I have my x and my 3 together, and my I pieces separate. So I'm going to group this as x minus 3 plus 2i. And I'm going to look at my x minus 3 as kind of a subset of my, it's really a trinomial, but I'm going to treat it like a binomial, using my x minus 3 as my first term in both binomials. So again, I'm going to regroup this one, so this one's x minus 3 as kind of a subset, my first term, minus 2i. And I just noticed that again, I should have not called that equals 0. I should have named the function y or f of x. All right, so now I'm going to distribute. Again, I'm looking at that x minus 3 as a single term. I'm not looking at it as a binomial. So I'm going to take all of x minus 3 times my first term over here, which is all of x minus 3. So I get x minus 3 quantity squared. And then I'm going to take my x minus 3 and multiply it by my negative 2i, but that will cancel with my positive 2i times x minus 3. So I'm not even going to write either of those terms. And then my last one, I'm going to take my 2i times negative 2i, which is negative 4i squared. All right, so to simplify this, I'm going to square my binomial. Remember, square means multiply it by itself. You cannot distribute a square into a binomial. Oops, that square shouldn't be there. Hard to talk and write at the same time. All right, so then I square out my binomial the same way I just squared out my previous binomial. X times x is x squared. Negative 3 times negative 3 is positive 9. So my middle term comes from the x times negative 3, negative 3x. We have two of them, so negative 6x. Simplifying my imaginary part, I squared is negative 1 times negative 4 is positive 5. Oops. And simplifying by combining my like terms, my final polynomial is x squared plus 6 minus 6x plus 14 equals y. So that's how we work with complex roots. We're going to take a look at irrational roots as well. This works the same way as all of the other ones. So the first thing that I note is we have an imaginary root again, which means it comes in a pair. So not only do I have x minus 2i, I also have x plus 2i for subtracting the negative 2i. So remember, one root is positive 2i, putting it in the asylum. The first one is minus. The second one would be negative, put it in the asylum, subtract a negative, and it's a positive 2i. And then I have x minus the square root of 2 once I put that in the asylum, and x minus 2. We'll call this one f of x. I remembered not to set it equal to 0 this time. Alright, so I'm going to distribute these two at a time. I'm going to distribute with my first two. I'm going to FOIL my first two, because then my complex numbers will go away. Again, when you've got the two binomials that look the same except for opposite signs, those middle terms will always cancel. So the x times x gives me x squared. X times a positive, x times a negative cancel, and the negative 2i times positive 2i, again, is negative 4i squared. This is still grouped together because I'm going to need to distribute that with what I get when I multiply these two binomials. So x times x gives me x squared, x times negative 2, negative square root of 2 times x, and positive 2 square root of 2. Alright, so my first binomial, I have x squared plus 4, because remember that I squared is negative 1 times negative 4. Here, I can't combine those two middle terms because I can't really add the square root with the integer. So I'm just going to leave this for multiplying purposes. I'm actually going to throw that x out front just because it's a radical. And then we distribute and simplify as much as possible. Alright, so x squared times x squared is x to the fourth. X squared times negative 2x, negative 2x cubed. X squared times x is x cubed, square root of 2. X squared, let's see, I'll do 2x squared square root of 2, just so that radical is always on the end. Alright, and then I need to distribute my 4, so I'm going to distribute it to each of the same ones. So we've got plus 4x squared minus 8x minus 4x square root of 2 and plus 8 square root of 2. I do have some like terms because I've got the same exponent on several of mine. When we combine them, I'm going to have to kind of do some grouping because of those radicals. So I've got one x to the fourth term, and I've got two x cubed terms. So here's what's going to happen when I group them. I have to group my coefficients together and then times my x cubed. Because my coefficients aren't like terms, I have to just do minus, parenthesis, 2 plus the square root of 2. And I factored out the negative. So yes, both my terms are negative, I factored it out, which is why I have a positive 2 and a positive square root of 2 in the parentheses. In this case, because of all these radicals, I would be okay if you left it in a kind of unsimplified form like what we just had after we multiplied. But I'll show you what both forms look like anyway. And then we've got a couple of x squared terms, same problem, one of them has a radical, so I'm going to factor those out. So we've got plus 2 square root of 2 plus 4 x squared, and then we've got two x terms. They're both negative, so again I'm going to factor out a negative. So we've got negative 4 square root of 2 plus 8x, and finally plus 8 square root of 2 equals f of x. Lots of fun once we get working with those radicals. Again, if you left it in this form, I would be okay with that. It's not any more difficult to read than this one. And the last thing I wanted to do was go over one more solving. So let's take a look at this one. Can we factor by grouping? I'm going to look at these two, and I'm going to look at these two. And I notice there's a GCF for my coefficients on the second two, but not on the first one. So once I pull out that 2, I am not going to have matching coefficients. So I don't see a way that factoring by grouping will work. So let's use the rational root theorem. P is 4, Q is 3. Factors of 4 are 1, 2, and 4. and the factors of 3, one of the factors of 3 is 1. So we've got all those integers to try. Sorry, trying to write too fast. That should be a minus sign. So I'm rewriting the factors of p because my second factor of q is 3. So those are all of my possibilities for rational roots. When I am checking for roots of a function, I don't immediately jump to those fractions. They're just not as fun to work with. My hope is always that 1 or negative 1 will work. So those are always the ones that I check first. Start by setting up the coefficients. We're not missing any, so we don't need any zeros. Drop the 3 times 1, add times 1, add times 1, and I'm not getting a remainder of 0 on this one. So negative 1 doesn't work. So now I'm just going to erase and start over again. Or sorry, positive 1 doesn't work, so now I'm going to try negative 1. Get a bigger eraser here. So now we try negative 1. Drop the 3, multiply, add, multiply, add, multiply, and again I am not getting a remainder of 1. So now I'm going to move on to 2. Again, instead of, I didn't know that 3 would be there, so I'll leave that this time. Instead of rewriting it and wasting a bunch of paper, or screen in this case, I'm just going to erase. So I'm going to try 2, multiply, add, multiply, add, multiply, not getting a 0. So let's try negative 2, see if we can fix this. So that would be a negative 6, so that would give me a negative 16, times 2 is a positive 32. So this is not going to give me a 0 either once I multiply by 2. I'm thinking one of those rational ones might be what we're going to end up with. Alright, so this is why graphing calculators are helpful. Sorry, I didn't look at this one in advance, so I didn't check the graphing calculator. I just have to try 4 because I want to try these integers before I jump to the fractions. That one's not going to work, so let's try a negative. And that one definitely will not work. Alright, so we have a rational one on this one. So let's start with 1/3. That one would be maybe a little bit easier to work with. 1/3 of 3 is 1. 1/3 of negative 9 is negative 3. And then when I get this, I'm going to get 7. 1/3 of 7 is not going to give me negative 4. So let's try negative 3. Negative 11, that'll give me a fraction, so that's not going to work either. Alright, sorry guys. I'm going to stop here because I've got 2 more fractions to try. And I didn't look at the graph, so I apologize for that one. What we're going to do on Monday is take a look at practicing these in class with the graphing calculators, so we don't have to do guess and check for 10 minutes. And then we will just practice a few of the, here are the roots, put them in standard form, write the polynomial.